We're going to learn a few theorems: the extreme value theorem, Rolle's theorem, and mean value theorem. But before we can do all that, we'll need to define what a critical number is and how we use those in those three theorems I just listed: the extreme value theorem, the mean value theorem, and Rolle's theorem. So let's first start by identifying extrema values. Extrema values are another word for the maximum and minimum values of a graph. There are four main classifications of extremas. The first pair are your absolute extremas, which is your global maximums or global minimums, and sometimes we'll use the word absolute. So you'll hear either global max or absolute max, and it means the same thing. So the second pair are relative extremas or local extremas. Again, those words are interchangeable. So let's identify some global extremas. So global extremas as the global maximum is the absolute largest point of the graph on whichever interval you're looking at. In this case, we're looking at the interval from A to F. And then, so our absolute maximum would occur at x equals d in this case. And our absolute minimum, the lowest point on our graph, will occur when x is equal to a. So those are the global or absolute maximums. Now let's find the relative maximums of this graph. So a relative maximum occurs when is the maximum point in a neighborhood or in a close interval. So one local maximum value would be at x equals b, because everything really close to it is lower or smaller than that value. Another local maximum will be at x equals f, because everything to the left of it, and that's an endpoint of this interval, is smaller than that value. Now let's find our local minimums. There are two local minimums on this graph. One is at x equals c, and the second local minimum is at x equals e. Now that we know what our extremas are, we can address our first theorem of the day, which is the extreme value theorem. This doesn't help us find where the extremas are, it just guarantees that there is an extreme or absolute maximum or absolute minimum on our graph. So if a function is continuous on a closed interval from A to B, then it will have both a maximum value and a minimum value on the interval from A to B. So basically, the extreme values theorem says if you have a continuous function on a closed interval, you're guaranteed to have both an absolute maximum and an absolute minimum. You might have more than one, but you'll guarantee to have one. So these three examples are examples where the extreme value theorem applies. So notice how in the first graph I have a continuous function. So at C I have an absolute maximum, at D I have an absolute minimum. Okay, my next graph is also continuous, and I have an absolute maximum at x equals C, and absolute minimum at the endpoint x equals B. For the pink graph, this is also continuous, so I'm guaranteed to have an absolute maximum and an absolute minimum. But in this case, my absolute maximum occurs at two x values because they are at the exact same height. So I have two absolute maximums, but only one absolute minimum at x equals D. Make sure you have a good understanding of the extreme value theorem. I want you to tell me if on the interval from 0 to 2, does the extreme value theorem apply? And if not, express why not. If it does, then find extremas. If it does not, express why it does not, and then determine any extremas that might still occur. Okay, because the extreme value theorem doesn't say there cannot be extremas, it just guarantees there are. So let's see how you did on A. Notice I have jump discontinuity at x equals 1, so it is not continuous on the interval from 0 to 2, so the extreme value theorem does not apply to this function. Even though the extreme value theorem does not apply, because of the point of discontinuity or the jump discontinuity, I still have an absolute minimum on this graph, and the absolute minimum occurs at x equals 2, but there is no absolute maximum. Now notice that it does appear that at 1, my graph is getting up pretty high. It's getting close to a height of 3, but it never actually reaches a height of 3. So since that open circle there, it can never actually reach that height of 3. So where do I pick off my maximum? I can't. So there is no absolute maximum for this graph. All right, try B. Yet again, the extreme value theorem does not apply to this function because it is not continuous at its endpoints. It's not continuous at x equals 0 because of removable discontinuity, and it's not continuous at x equals 2 because of infinite discontinuity. So I cannot apply the extreme value theorem. I'm not guaranteed absolute maximum minimums. Now looking at the graph, I see that there is not an absolute extrema at all for this graph, because the lowest point is approaching that open circle of 1 but never actually reaches that point. So we do not have a absolute minimum, and we do not have an absolute maximum because my graph continues up to infinity and never reaches a maximum point. Okay, see, there's another example where the extreme value theorem does not apply because we have, again, jump discontinuity and x equals 1. But even though we have jump discontinuity and we cannot apply the extreme value theorem, this function actually has an absolute minimum and an absolute maximum. The absolute minimum occurs at the point x equals 0. And the absolute maximum, the highest point on our graph, occurs at x equals 2. D, the extreme value theorem does apply. It doesn't apply, sorry, I said does. Doesn't apply here because we have removable discontinuity at its endpoints. It's continuous everywhere except for its endpoints, but our formula says it has to be continuous over the closed interval, as you can see. So we have removable discontinuity. But even though we have removable discontinuity and the extreme value theorem doesn't apply, we still have absolute max or mins. And our absolute maximum occurs at x equals 1/2, and our absolute minimum occurs at x equals 3/2. So the extreme value theorem only guarantees an absolute maximum minimum if you have a continuous function on a closed interval, but it doesn't tell you where they're at. And it doesn't disclude any absolute maximum minimums of functions that don't meet the extreme value theorem. So now we're going to look at something called critical numbers. Critical numbers are going to be extremely important in this entire unit, so we make sure we have a good understanding of that. So if the derivative equals 0, or if the function is not differentiable at x equals c, then we say c is what we call a critical number of f. So that's our official definition. Critical number occurs when the derivative equals 0 or the derivative does not exist. So another way to state this is if f has a relative maximum or a relative minimum at the point x equals c, then we say c is a critical number. So critical numbers occur when the derivative equals 0, the derivative does not exist, and only at critical numbers can you have relative maximums or relative minimums. So relative maximum minimums occur only at critical numbers. So that's why it's so important for us to know about critical numbers. So now that we've known how to figure out critical numbers graphically, so now look at this graphically. I have a horizontal tangent line, so that at my local maximum here, so my derivative equals 0. And notice all my local maximum or my absolute maximum here, my derivative is also equal to 0. And our relative minimum here, our derivative is equal to 0. So that's an example of where the derivative is equal to 0 gives us a relative maximum minimum. Sometimes the relative maximum could be the local maximum. Now here at x equals c, we have our derivative does not exist because we have a sharp turn. And so this is an example where you have a critical value and a local minimum at where the derivative does not exist. So critical numbers on this graph would be the b, c, d, and e. Now that we know how to find, we've figured out how to find critical numbers graphically, let's figure out how to find critical numbers algebraically. And so to find your critical numbers, you're again going to start by finding your derivative. So let's differentiate f of x using our quotient rule. That's low d high minus high d low over low low. Simplifying this down, we determine that our derivative of f of x is equal to 4 minus 4x squared over x squared plus 1 quantity squared. Now, to find the critical numbers, we need to figure out when our derivative is equal to 0 and when our derivative does not exist. So for rational functions, to find where the derivative equals 0, I just set my derivative equal to 0. And for any rational function, your derivative is equal to 0 when the numerator equals 0, because if I multiply both sides by x squared plus 1 quantity squared times 0 just gives us 0 again. So solving this equation for x, we get that x is equal to plus or minus 1. So next I need to figure out when our derivative does not exist. For rational functions, our derivative will not exist when the denominator equals 0 because you cannot divide by 0. So I would set my rational function, my derivative, and I want to figure out why that does not exist. So I would figure out when the derivative, the denominator equals 0. And then, oh wait, if I square root each side, I get equals 0, but then I have x squared plus 1 equals 0. Well, when you square a number, it's always going to give you positive, so there's no way that that x squared plus 1 squared is ever going to be 0. So our derivative does not exist, and so we only have two critical numbers for this problem, x equals 1 and x equals -1. Now it's your turn. Let's see how you did. So first you want to start by finding the derivative of f of x, which would be 4x cubed minus 16x. To find the critical numbers, you need to figure out when the derivative equals 0 and when the derivative does not exist. So first we're going to start by setting our derivative equal to 0 and solving for x. So I'm going to do this by factoring out our GCF and then factoring the parentheses by doing the difference of squares. And we find three critical numbers at x equals 0, x equals 2, and x equals -2. Then I'm going to look where the derivative does not exist. Well, f of x, our derivative is a polynomial. And since it's a polynomial, it is differentiable everywhere. So this does not apply in this case. Our derivative will always exist. So therefore, my conclusion is the critical numbers of f of x are at x equals -2, 0, and 2. Now that we know how to find critical numbers, we're going to use these to find the extremas on a closed interval. And this is our absolute maximums, absolute minimums on a closed interval. The steps to find the extremas when you're given a closed interval are the following. Step 1, find all your critical numbers by doing what we just learned in our previous examples. Then on step 2, you're going to evaluate the function at each critical number. So that's taking each critical number and plugging it back into your original function, f, and figuring out its function value, the y value. Then we're going to evaluate the function at the endpoints of the interval. So we're going to plug it back in, plug a and b, our endpoints, back into our original function. Then we're going to look at these y values. The least of these values is going to be the minimum value of our function, and the greatest is going to be our maximum value. So that's how you determine the minimum and the maximum. On a closed interval, it will only occur at your critical points or at your endpoints. So let's try our first example here. So I'm going to start by finding the derivative of g of x. Now, in order to differentiate a cube root, I need to rewrite this as x to the 1/3 power. Then using my power rule, I get that the derivative is equal to 1/3 x to the -2/3. And then let's get rid of our negative exponent by moving the x down and put it back in radical form. And then get my critical values. That's when our derivative is equal to 0 or when our derivative does not exist. So our derivative equals 0 for a rational function. Again, the only time a derivative will be equal to 0 is when the numerator equals 0, but 1 will never be equal to 0, so that one is thrown out. Okay, now I'm going to find where our derivative does not exist. So for a rational function, the derivative will not exist when the denominator equals 0. So when we divide by 0, so I'm going to set the denominator equal to 0 and solve for this. And we find that it occurs at x equals 0. So we have one critical number for this function, and that is x equals 0. Now I'm going to go back to our step 2. We're going to evaluate our function. So we go back to our original equation, not the derivative, back to the original. And I'm going to evaluate it at x equals 0, our critical number. And I get 0. Then I need to evaluate our original function at our two endpoints, so at -8, and I get -2. And at 8, I get +2. Then I'm going to compare these answers, 0, -2, and 2. My smallest number will be where my minimum value occurs, and my largest number is my maximum value of this function. So my conclusion is that g of x has an absolute maximum at x, absolute maximum of 2 at x equals 8, and g of x has an absolute minimum of -2 at x equals -8. Now, sometimes you'll see the answers written like this, and this is completely legit. A lot of books like to write the answer like this, but other times you will see it put together as a point. So you'll see that you'll say something like this: g of x has an absolute maximum at the point 8, 2, and g of x has an absolute minimum at the point -8, -2. So be aware, be able to write it either way, and on multiple choice, I might write it either direction. So make sure you can recognize what those two terminology means. All right, your turn. All right, so we're going to try to find the absolute extrema of this function on the closed interval from -1 to 6. So we're going to start by differentiating h of x by using our quotient rule. Low d high minus high d low over low low. Simplifying that, I figure out that my derivative is equal to 3 divided by t plus 3 quantity squared. And then our critical value, remember, is when our derivative equals 0 or our derivative does not exist. So let's figure out when our derivative equals 0. Again, it's a rational function, so derivative will be equal to 0 and the top equals 0, but 3 will never be 0. So we throw that one out. Then we figure out when our derivative does not exist. Well, our derivative does not exist when the denominator equals 0. And if I square root each side, I get t plus 3 is equal to 0. Subtract the 3, subtract it, I get t equals -3. But -3 is not in the interval of -1 to 6. So therefore, in our given closed interval, there are no critical numbers. So all I have to do is evaluate our original function at our two endpoints to figure out which is our maximum and which is our minimum. So since -1/2 is smaller than 2/3, our minimum occurs at the -1/2 and our maximum at 2/3. So our answer is we have an absolute minimum at the point -1, -1/2, and we have an absolute maximum at the point 6, 2/3. When we're looking only at our interval from -1 to 6. I'm going to go ahead and put in why this one does not exist, just in case you didn't have that information. I said it, but kind of thinking about it, you might want to have it in your notes, the reason why, because it's not on that interval. If my interval had been different, I might have it. All right, so our second theorem of the day is called Rolle's theorem. Rolle's theorem is pretty cool. Basically says, let f be a continuous on the closed interval from a to b. So continuity is still required. And differentiable on the open interval from a to b, not including the endpoints. So our two requirements for Rolle's theorem must be continuous and differentiable. Our third requirement, that the f of a must equal f of b. So the function value at your two endpoints have to be the same. So it has to be at the same height. Then our conclusion is that there is at least one number, which we'll call c, in the interval a to b, such that the derivative at c has to be 0. So it has to be one point where the derivative equals 0. All right, so let me give you some graphical representation of what's going on here. I'll give you a couple. So I'm on the interval from a to b. So let a be here and then b here. And then let these 2 points be our beginning and ending at the same height, and that's at f of a and f of b is that height. So they have the same height. So this Rolle's theorem says, if I have a continuous function that is differentiable everywhere, so no sharp turns or corners, but it's continuous, so something like a smooth curve here, there's guaranteed some point on this graph, which I'll call c, where our derivative is exactly 0. Now, this guarantees only at least one number c, so there might be more than one, and that's what I'm going to show in this second example. So again, I'm going to start my a and b, and my endpoints are at the same height, so let me put my endpoints in at the same height. Then I have a continuous function that's differentiable everywhere, so I'm just do some nice smooth curves here. And so here I have 3 values that where our derivative is equal to 0, and I'll just kind of dot those in. So let's see how we can apply Rolle's theorem. So we're going to determine whether Rolle's theorem applies to the given function. So remember our 3 conditions for Rolle's theorem. Our 3 conditions are it must be continuous, it must be differentiable, and the function values at the endpoints must be the same. And if the Rolle's theorem does apply, we're going to find our actual c value on that interval that the derivative is equal to 0. So we're going to start by, of course, differentiating this. Oh, so I'm sorry, we haven't proved continuity yet. So we're going to start by proving continuity. So I just wanted to see if I could cancel anything out, simplify this. Then I'm going to find my domain of my rational function. So remember, our domain is everywhere except where the denominator equals 0. So in this case, everywhere except 2. -2 isn't in our interval from -1 to 3, so it is continuous on that interval from -1 to 3. So we prove continuity on a closed interval. Okay, next I need to prove that it's differentiable on that closed interval. So in order to prove differentiability, let's find the derivative of f of x. We'll use the quotient rule. So our derivative is equal to x squared plus 4x minus 1 divided by x plus 2 quantity squared. And so when is this derivative differentiable? It's differentiable everywhere except when the denominator is equal to 0. So the derivative will not exist when the denominator equals 0. So in this case, that will be at -2. But again, -2 is not in our interval, so therefore we can conclude that this function is differentiable everywhere in the open interval from -1 to 3. That should be an open interval, not a closed interval, my mistake. So now that we know we have continuous indifferentiable, now we need to make sure our third requirement is that our function values at the endpoints must be equal. So I'm going to evaluate my original function at -1. And I get 0 divided by 1, which is 0. And I'm going to evaluate my function at 3. And it is also equal to 0. So I've met all three conditions of the Rolle's value theorem. So therefore, all I need to do is now figure out where my derivative is equal to 0. And wherever that derivative equals 0, that will be our C value. That's guaranteed. So recall earlier we found that the derivative of f of x is equal to x squared plus 4x minus 1 divided by x plus 2 quantity squared. So this will equal 0 when the numerator equals 0. This quadratic does not factor, so I'm going to use the quadratic formula to solve. I can write the square root of 20 as 2 to the square root of 5. And then factoring out our GCF of 2 and simplifying down, I get -2 plus or minus the square root of 5 divided by 2. And then kind of punching this into my calculator, figure out if it's in my interval or not. I'm going to take -2 plus the square root of 5 divided by 2, and I end up with 0.118. And then I'm going to take -2 minus the square root of 5 divided by 2, and I get -2.118. -2 is not in that interval, but 0.118 is. So my conclusion is the C value guaranteed by the Rolle's value theorem is -2 plus the square root of 5 divided by 2. Your turn to try this one. All right, so we're going to start in figuring out if the Rolle's theorem applies to this problem or not. So again, we need to prove continuity and differentiability. So first, to do continuity, since it's a rational function, I'm going to find the domain of the rational function. And our domain is going to be -infinity to 0, union 0 to infinity. So it's discontinuous at 0. 0 is in the interval from -1 to 1. So my conclusion is the Rolle's theorem does not apply here. End of problem. Now, Rolle's theorem, notice if I did the slope of the secant line connecting our two endpoints of our Rolle's theorem, that would have been 0, and then we found a point on our interval where the derivative is equal to 0. We're going to expand the Rolle's theorem to include now the mean value theorem. Now, the only difference between the mean value theorem and the Rolle's theorem is that in the mean value theorem, the function value at a and b does not have to be the same. So the only conditions are going to be that it must be continuous and differentiable. So let's say f of a is up here, while f of b is down here. So the f of a and f of b is not equal. As long as I have a continuous function that is also differentiable connecting those two endpoints, so I'll just draw a smooth curve. The mean value theorem states that there exists some point C on this interval such that the slope of the secant line, the slope of this line I just drawn through my endpoints, is equal to the slope of my tangent line. They'll be parallel. That's all mean value theorem says. So the slope of the tangent line, and that point of tangency is at x equals c, it equals the slope of the tangent line when we draw the slope, the secant line, slope of the secant line, when the secant line is drawn through the endpoints of our interval, our closed interval. Now again, this only says that there exists at least one c. There might be more than one c, as I'll draw in this second example. So I'll start my f of a and my a point and b point at base the same point, but again I have a continuous differentiable function. And there, all this says is that the slope of the secant line is equal to the slope of the tangent line at the point C. In this case, we have C1, C2, and C3. So there are 3 C values that this works. So let's get this formal definition written down. So this is the mean value theorem. If C is continuous on the closed interval from A to B, and differentiable on the open interval from A to B, there exists a number C on the open interval such that the slope of the tangent line, and what's our calculus notation for slope of tangent line? That's the derivative at C, equals our slope of our secant line. That's the change in the y, so that's going to be f of b minus f of a, divided by our change in our x's, b minus a. So again, that's all the mean value theorem. If you have a continuous differentiable function, there exists some c in the interval from a to b such that the slope of the secant line equals the slope of the tangent line. So on this example, we determine whether the mean value theorem applies. The only two conditions must be continuous and differentiable on this closed interval from a to b. If the mean value theorem can be applied for our derivatives, we're going to find all values of c on the open interval that meets the requirements of the theorem. So f of x in this case is a polynomial. We know a polynomial is continuous everywhere. So therefore, we can say it's continuous on the interval, the closed interval from -1 to 1. So it meets our first requirement of the mean value theorem. Then we can differentiate this by using our power rule, get 3x squared plus 2, which happens to be a polynomial as well. And we know that polynomials are differentiable everywhere, so therefore it's differentiable on the open interval from -1 to 1. Yes, we have now met the two conditions of the mean value theorem, so the mean value theorem will apply to this problem. All right, so the mean value theorem formula is the derivative at c is equal to the slope of the secant line, which is our change in our y, so f of b minus f of a, divided by our change in our x's, b minus a. So over to the side, I'm going to figure out f of c. F of c is just my derivative, which is 3x squared plus 2, which is replacing every x with c. Then I'm going to find my function value at b, and b in this case is my endpoint of 1. So I'm going to replace every x with 1 in my original equation, and I get 3, so f of b is 3. And then f of a is my other endpoint, my beginning point. So I'm going to replace every x with -1 in my original function to get -3. And then, of course, b is 1, a is -1. Then I'm just going to simplify and solve this equation. So 3 plus 3 gives us 6, and 1 plus 1 is 2. 6 divided by 2 is 3. Solving for c, I'm going to subtract 2 from each side. That gives us a 1. Divide each side by 3. And then square root each side and rationalize the denominator. And I get that c is equal to plus or minus the square root of 3 over 3. Now I need to check and see if these are in the interval from -1 to 1. Well, the square root of 3 divided by 3 is within that interval. It's like a 0.5 something or negative 0.5 something. So c is our values that are guaranteed by the mean value theorem. So at the square root of 3 over 3 and at negative square root of 3 over 3, the slope of the secant line is equal to the slope of the tangent line. Your turn. So again, we're going to start by finding if this is continuous. Now remember, our rule of continuity is if one function, a continuous function plus another continuous function equals continuous function. So I'm going to look at each of these separately. So cosine of x is continuous everywhere. So it's continuous on that interval, but tangent of x, if you remember from our graph of the tangent function, it is discontinuous at pi over 2 because we have an asymptote at pi over 2, and pi over 2 is between 0 and pi. So therefore, this function is discontinuous on this interval, so the mean value theorem does not apply, and we can stop.